Right, next speaker is Peter Grindrod from Birkbeck College, selecting the landing site for ESA 2018 ExoMars rover. Peter.
Thank you, good afternoon. I imagine most of the talks that you hear at ordinary meetings are along the lines of the one we just heard about Planck, which reflect many years of work by many people, maybe covering an entire mission or entire career. And it's probably fair to say that my talk isn't going to be like that. Instead, you're going to hear a very ongoing report of where we are in terms of selecting a landing site for the ExoMars rover. Most of the new results you'll see today have come out of only the last 3 or 4 months and will carry on for the next couple of years. But I'm talking here today as part of a UK consortium of scientists that came together back in December. And this is Sanjeev Gupta, John Bridges, Matt Baum, John Wachowski, Peter Forden, and Jan-Peter Muller. And we came together after ESA issued this call in December to propose landing sites. And so I want to take you through, this is ExoMars, this is the rover, in case you hadn't guessed already. And I want to talk you through some of the background that goes into our thinking, the constraints that we've been working under, the science that drives it, and ultimately where we're heading, or where we might be heading. Okay, so let's start with the scientific objectives of the ExoMars mission. And there's 4 main ones: to search for signs of past and present life on Mars, to investigate the water and geochemical environments with depth in the Martian surface, to study the Martian atmosphere, and to characterize the surface environment. And now, to my mind at least, the constraint which is most important in terms of deciding where to land on Mars is that first one, the search for life. I'd think that those last 3 could probably be addressed in most places on the planet. Most of the control comes from that first constraint. And so over the last, say, 10 or 15 years of Mars exploration, the thinking has been, the mantra has been for Mars, follow the water. And the thinking is there that without water, there isn't life. And, that may well be true, but it's probably not the whole story. Instead, over the last few years, with Curiosity leading the way, Curiosity's mission is designed to look at the habitability of its landing site, Gale Crater. ExoMars is actually going to be looking for signs of life, and the 2020 rover by NASA may well be caching a sample to bring back to the Earth. And so it's a different way of thinking now. It's not just follow the water. We talk about redox reactions rather than just if it looks like a channel. And I would say that the reason, we can talk about this later, but it's a controversial statement maybe given my audience, that I would say the reason that these expensive missions are sent to Mars is because Mars still offers the best chance of finding life in the next few decades. And this is finding life is my caveat that we can discuss later on. But given the audience, I thought I might as well do a little bit of astronomy. This is as much about astronomy as I know. This is Mars through a telescope from the surface of the Earth, admittedly quite a good telescope, I think. And don't get me wrong, this is a phenomenal image and one that I would love to look through a telescope. But as a planetary geologist, it doesn't quite cut it if you want to understand the planetary evolution and actually look for life. You can't really tell those things from this sort of distance. So we have to get closer if we want to learn those things. And so to do that, we send spacecraft. And we've sent quite a few since the start of the space age. Now, I don't want you to read all of these. The most important thing to note here are the colours. So from 1960, the start of the space age, through to the present day, these are all the missions that have gone to Mars, and red means it was a failure, green means it was a success. And so, most people know that over half of the missions to Mars have failed over the years. And so this shows that what ExoMars is trying to do, or what ESA is trying to do with ExoMars, is actually a very difficult thing. It's not easy to land on another planet. And so this is a kind of a bold goal that they kind of set. But you can also see that most of these failures came in the early days of the kind of space age, and mostly on the Soviet side as well, but NASA has had great success in the last decade, particularly some landed missions, and ESA as well with Mars Express. Okay, now, hopefully most people have seen this image before, but just in case you haven't, I'm going to explain it briefly because I'm going to show it a lot in the next 10 minutes or so. So to set the background for where we're going to land on Mars, I have to tell you a little bit about the global geology. So this is the entire globe of Mars. We're looking at from North Pole to South Pole and the entire range of longitudes. So hopefully some of you recognize these features. This is a map of the elevation, the height. So the purples and the blues are low, the browns at the higher elevation. So you recognize the Tharsis Bulge, the Tharsis volcanoes, the Olympus Mons volcano, which I keep banging this drum about. Everyone knows Olympus Mons is the biggest volcano in the solar system, but in terms of height only, in terms of volume, Albertera wins that game, but it won't win you the pub quiz question. Valles Marineris, this huge canyon system, this is what I consider to be my field site on Mars, where most of my research is carried out. From there, these huge outflow channels flow to the northern hemisphere, the low area, and it kind of shows the first order difference here on Mars, where the northern hemisphere is low and relatively flat compared to the southern hemisphere, which is higher and has more craters. So if you map out those craters, and the latest database is almost 400,000, and they're only the ones above a kilometre, you can see that it's true. Most of the craters, and the larger craters, occur in the southern hemisphere. So knowing what we know about the formation of the solar system, where there are more impacts happening earlier in the solar system's history and then they decline through time, then that shows that when you map out the geological units, you can get an age of the unit on the surface of Mars, and that's been calibrated from the samples brought back from the moon. So this is what geologists have kind of put together over the last, since Viking, basically. And it's a geological map of Mars on the broad scale showing the different age units. And so here we have Mars's entire geological timescale from 4.5 billion years ago to the present day compared to the Earth's. And you'll see that it rings true. Most of the blue, the old terrain in the Noachian, I'm going to make you remember these names because I'm going to talk about them a lot. This represents material that's probably formed up to about 3.7 billion years ago. Then the greens, the Hesperian, they occur from 3.7 to 3.1 billion years. They represent the middle part of Mars's history. And then for about the last 3 billion years or so, we've got these oranges, the Amazonian period. And so, as well as mapping out the units with the craters, over the last 10 years or so, we've made a great advance in near-infrared spectroscopy of the surface. Now, don't forget, this is a planet that has an atmosphere, largely CO2, can be quite dusty. There's also some water vapor sometimes. You're looking at a surface that is actually covered in dust as well. So to get out nice spectra that you can actually learn something about the geochemistry of the surface is actually quite impressive. Nonetheless, these kind of points represent some of the sites that have been identified that represent different chemistries of the surface. So you can see in blue areas that correspond to phyllosilicates or clay minerals. Now from the Earth, we know that these clay minerals form when you have a basaltic precursor rock. You have water that alters that rock and it forms these clay minerals. That water, to form clays, tends to have a neutral pH. So the paradigm that's emerged for Mars is that early in its history you had quite a bit of water around that was neutral in pH. It was maybe a bit warmer too. This represents a habitable period in Mars's history. Then in green and yellow you can see these parts correspond to where we have hydrated sulfate minerals like gypsum or Epsom salts on the Earth. And these sulfates form in a similar way, but this time the water is probably acidic in pH. And so you've had a transition here from what could well be a habitable period in Mars's history to a less habitable period through a combination of Mars maybe losing its magnetic field, the volcanoes spewing huge amounts of volcanic gases into the atmosphere. And so the story out of this that I want you to remember is that if you want to go to the most habitable parts of Mars, you're probably going to have to target the oldest places you possibly can, because that's where you stand the most chance of getting there. Okay, so let's move on to ExoMars. Now, in terms of the constraints, this is coming back to the old cliche of it's a delicate balance between the engineering constraints and the scientific goals of the mission. But if you take the whole planet, let's say we've got 100% of the planet available to us, this is similar to pretty much almost the Earth's continental landmass, given that we have oceans on the surface. So we've got 100% available. The first main constraint for ExoMars is that it uses a parachute to slow down in the atmosphere. Mars' atmosphere is about 100 times thinner than the Earth, so that parachute needs as long as possible to slow it down. That means you have to land at low elevations. For ExoMars, that means landing below about minus 2 kilometers with respect to the mean elevation of the planet. So now we've only got 59% of the planet available to a scientist to choose a landing site. Still 3 times the size of the Asian continent now. The next one is that ExoMars is going to land between this latitude constraint of between 5 degrees south and 25 degrees north. And that's a combination of it needs the solar power near the equator, but also it's a temperature constraint on the rover. So now we're down to about 10% of the surface to choose. And then the constraint of science. We need to hit the oldest regions, so things that are Noachian and possibly at the Noachian-Hesperian boundary, about 3.6 billion years or older. And that leaves us these green areas. That's all we've got left of the planet now to choose from. And this corresponds to about 2% of what we started off with. But still, 2 times the area of, say, Kazakhstan, which is an enormous country. Okay, but also landing on Mars isn't a pinpoint process. There's uncertainties in the descent through the atmosphere that mean that there's a certain probability of landing within a certain distance of your target on the surface. And that's called the landing ellipse. For ExoMars, it's about 104 by 19 kilometers. And this is very similar to the ellipses of Spirit and Opportunity. There's also an added complexity for ExoMars, is that, well, all missions, in fact, that the angle of these ellipses depends on when you launch in your launch window. So for a 2018 launch, we have ellipses that vary between these 2 yellow here. We can land anywhere in there, but we have to fit both in. If there's a backup launch in, say, 2020, the angle of these ellipses can change even higher, and we have to accommodate all of these blue ellipses. So to kind of give you some sense of scale, let's say that ESA decided to land their rover in the northwest of England because everyone knows it's the most habitable place in the solar system. And let's say you wanted to target Manchester, because why not? And you've got the problem here that if you wanted to land in Manchester, you may well end up in Liverpool if you landed short. But to be honest, most of these missions tend to land long. We're going to be coming in from the west, so we're going to be heading towards the long end of the ellipses, and you may even well end up on the wrong side of the Pennines. This is a serious problem. So we've had the task of taking that global map, taking these ellipses, and trying to find areas that are scientifically interesting that can meet the goals of the mission. So that's what I'm going to talk to you about now. These are the constraints for ExoMars. Plotted over the top. They're not too bright, but I hope you can still see them. In green are successful landed missions on Mars. Red are the failures. And you can see that with the possible exception of Viking 1, none of the previous landing sites kind of fit the criteria that we set. Most of those come from the age, to be honest. That's quite a bold aim. And so this is exciting. This means that this is going to be really new territory that ExoMars is going to be exploring, somewhere we've never gone before. I think this is fantastic. So back in December, this is the timeline of what we've done. Back in December, ESA issued a call for landing sites. That's when our consortium got together. We put in quite a bit of work. We looked at 28 initial candidates just within our own consortium, mostly clustered around here, around kind of Circum Crissy Basin, a couple over here near the Isidis Basin. Those proposals were due in February. This is quite a lot of work we put in over a couple of months. There were actually 8 official proposals put in. We led 2 and were involved in a third one. And it's quite nice to see that the proposals put in actually match pretty much where we were looking as well. So that's kind of shows we're on the right lines. And then back in March, the first landing site workshop occurred in Madrid. And the proposers came together for 3 days. They proposed their sites, they discussed them. And the landing site working group put in a great amount of work to kind of ask the right questions of the groups as well. And so at the end of that meeting, 4 favourites appeared. Now, I've called them favourites because these aren't the final 4 yet. The official list will come out later this year. ESA will announce them. Up to 4 sites. It may well be the same. There might not be as many. But these are the favourites that emerged. Mars Vallis, Oxypalus, Oxyplanum, and Epanis Vallis. And I want to briefly take you through each of these sites and try and show you some of the pros and cons of each one and what it might be like if we go there. So this is zooming in. You can see that the 4 favourite sites actually occur in quite, well, the same part of the planet. This is kind of Circum Crissy Basin. This is the transition from the highlands to the lowlands, the dichotomy boundary. And the black represents elevation that's too high. We've got Mars Vallis up here in the north, Oxypalus. Both these sites, you can see, are squeezed in amongst kind of some high elevation. So both of these are on almost at the limit of where we can go in terms of elevation. But Oxyplanum, Epanis Vallis are both fine. They're much, much lower. And they're both, all of them lie quite close to these huge outflow channels. Aris Vallis here flowing out to Crissy. So I'm going to take you through a tour of these quickly from Mars Vallis heading south. Okay, now, so starting with Mars Vallis. Now, I imagine some of you have heard of this before. This is the real heavyweight in terms of the landing sites. So, this got through to the final 4 for the Mars Science Laboratory. There's been a lot published on this already. It's a very well-studied site. But it's important to note that ExoMars wouldn't go to the same place that was proposed for MSL. We're actually a little bit southeast down. This is Mars Vallis itself. It came later. The rover wouldn't be looking at that and actually can't because the slopes are too steep here. But you can see we've had to get quite creative with the ellipses here as well, and we've really juggled them about and moved them so they can fit into this safe area. Again, black is elevation we can't land on. But this area that the ellipses occur in is absolutely chock full of those phyllosilicates, different compositions and amazingly diverse mineralogy in this region. Really interesting, full of layer deposits that the drill on ExoMars can get to. But I'd say that, in my opinion at least, one of the cons may well be for a Marth is that it's too complex. There's so much going on here that actually we're not sure how it formed. There are a few different hypotheses, and will we be in a state where we can predict what we can test with ExoMars? I'm not sure, but it's a really interesting area. Second, working down, Oxyplanum, you could consider this to be an extension of Marth Vallis if you want. The story here is the same. It's that of clays. These two images represent some CRISM data, so near-infrared. This is a false colour image, and this is some spectral parameter maps highlighting the kind of mineralogy you're getting. Remember I said this is a dusty planet, and yet the mineralogy here is screaming out at us that these things are rich in iron magnesium clays, aluminium clays, all that can be mapped out in about 100, maybe 200 meters of layered rocks that can be accessed by the rover, by ExoMars. So the story is kind of similar. Oxyplanum might actually be safer than Marth Vallis, but again, there's that question about how it formed and can we actually ask a good question in this region. Moving down to Hapanis Vallis, it's one that most people will be able to understand, I think, quickly. And basically, there's channels that come in from the south. You can't see that. And they end in this kind of lowland area here, and there's basically some kind of fluvial delta systems that have deposited material. And deltas are fantastic for depositing and concentrating organic material that you might be looking for if you're looking for life. And we can also make a confident prediction that there should be similar mineralogies here, those phyllosilicates. We've identified them here in the west, and we think they may well occur in the east, but we haven't got the image data yet. We're requesting it. And we've actually shifted these ellipses a bit to the west because there's a question about the slopes on some of these small mesas as well. So there's an issue about slopes here, but hopefully we can address it by moving it west. Then Oxyopalus. Here we're not looking at a kind of an erosional channel or clays. Instead we're looking at this feature here, which is basically an inverted river system. There was a river flowing through this area probably about 4 billion years ago over a long period of time, very similar to like we see in the Green River in Utah. And basically everything around the river gets eroded away and you're left with this hardened material, leaving the sinuous channels behind. And again, we're lacking mineralogy information in this region, partly because we don't have much data here, but also partly because it might be dusted in the other sites. So that's something we need to work on before our next workshop if this site gets through. And as an example of some of the work that's gone in, not just by our team and our proposals, but every proposal that was put in, every site, some of these were brand new. Marth Vallis, dozens of papers already. Oxyopalus, so little work had been done on this that actually Oxyopalus is the name of the much broader region. Nothing had been named in this region, so we've actually applied to name this feature. And we actually applied to name it Irwell Vallis after the Irwell River, which runs near Manchester and quite close to my house. But it's been turned down because this isn't an erosional feature, which is what valleys are named after. Instead, it's an inverted channel, so this may well be called something serpentes. So watch out for that. Hopefully in the next few months it might get a name. But we've done some preliminary mapping. We didn't have anything before then. We've mapped out some different units. We think there are probably alluvial deposits either side of this channel. They'll be what the rover was targeting, not the actual channel itself. We've carried out crater counts where we count thousands of craters on different units, work out the age. We're pretty sure that these are ancient river deposits. They've been covered by impact ejecta, and we can date that ejecta to about 3.7 billion years ago. And then we're pretty sure that this stuff has been eroded starting about 500 million years ago. So it's been exposed for a relatively short period of time, which is good if you want to preserve organics because they're broken down by UV and by radiation. We've also carried out some, the infrared spectroscopy, looking at squiggly lines in the spectra. Loads of kind of the engineering safety analyses, so elevation, slopes, albedo, thermal inertia, slopes on different scales, wind. There's a lot of things to consider, and all of this was done in about 2 or 3 months. It's a great effort by everyone on the teams and by the working group who had to sift through all of our work as well. So I'm coming to the end now, and I want to kind of say, so ExoMars, where's it going to? This is a timeline. of where we are. We're kind of in between the workshop and this says the decision on the final 4, up to 4 sites. There'll be a few more workshops, but at the moment there are 4 favourite ones. There's a lot of work to do in the next few months or maybe a couple of years when we go to these workshops and present them. And I think that one of the things that we'll hammer out over the next couple of years is, in terms of each of these 4 sites, we need to figure out the habitability or the chances of finding life at the different sites. And it comes down to maybe the difference between the case that mineralogy makes for life being there or the case that geomorphology makes. I think there's probably both at all of these sites. It's not a problem. But it's working out the relative strengths of the different sites. And at the same time, we've got to make sure that we still match all of the elevation and slope engineering constraints along the way. And the almost final decision will be made in mid-2016 by ESA and Roscosmos. I can't say it's a decision that I envy, but that will be based on recommendations from the working group who have been at all of these workshops. But the analysis is, I want to make this point out, and I think it's important, and it's something that was mentioned at the workshop too. This is analysis that is carried out by lots of different people. It shouldn't be a case of it's one site or it's one group site or it belongs to anybody else. It doesn't. When that final decision is made, kind of the end of 2017 and ExoMars will launch early 2018, I really hope that kind of Europe considers this to be our landing site, because rather than, I've put a blank background here for ExoMars because we get to choose where this thing will be drilling and maybe possibly finding life as well. I think this is tremendously exciting. So hopefully everyone will get behind the kind of process of choosing and the final decision as well, because I think it's going to be extremely exciting. And I'll stop there. Thanks.
Right, questions? Miles. Use the microphone.
ALH 84001, its 4.5 billion year age, makes the place that it came from especially interesting. Just like on Earth, a lot of effort goes into looking at the very oldest patches of crust we can find. Is there any possible indication of any place that would be preferable to explore in order to find a place that the crust like what it came from, because it's only been exposed for 20 million years in space. So quite recently, there has been that sort of crust exposed.
Yes. So you could narrow down broad regions where it might have came from matching the composition with the limited spatial composition we have of the surface. The age stuff is kind of easier to do, although when you start looking at small areas, your age estimate starts to become a bit iffy because the errors on small areas are quite large. In terms of ExoMars targeting an old area, well, it's kind of a double-edged sword. Although it's difficult to explore Mars because it's a different planet to the Earth, actually, if you want to try and access old rocks, it's actually maybe easier to get to them on Mars, because on the Earth, we've had 4 billion years of plate tectonics and water and erosion and a lot of life that makes the oldest rocks are chewed up, hidden, recycled. On Mars, you may well be looking at some of the oldest crust. So I think there's more of it around, which matches up with meteorites as well. But finding where those specific meteorites come from, I think we're probably not there yet. Although some people kind of think they can narrow it down a bit.
Okay.
Excellent talk. But to coin a term, I'm probably going to get shot for saying this. Why are we sending yet another rover to Mars when we've got a giant ball of ice orbiting around Jupiter? We've literally got a moon around Saturn that's spitting out water, and you've also got Titan, which has got oceans of hydrocarbons in there. So why are we going back to this dry, barren rock?
So this isn't a plan. I think this goes back to one of my second slide where I said the best chance of finding life remains with Mars.
You're allowed to shoot him.
No. I've got a laser pointer. No.
Please don't shoot me.
So my caveat here, and I think the answer to your question is finding life. I would never argue that there aren't some fantastic places in this solar system and other solar systems where life might have existed or still exist. And Europa, Ganymede with their oceans, Titan with their ocean, and Enceladus with its ocean are fantastic locations. The question comes down to conclusively finding evidence for life. You have to find evidence that you can hold up and say, I'm confident. You know, Viking taught us that even with instrument results that you said beforehand, if they were positive, it'd be life. You can go back and say, actually, we're not sure. So this comes back to Carl Sagan popularizing the philosophical quote, extraordinary claims need extraordinary evidence. To find that extraordinary evidence, I'm not sure you can do it with a flyby mission or even landing on the surface of an icy moon, because the habitable environment is actually in the ocean, which is at least 20 kilometers away, 30 kilometers away. So I think the best chance of finding life is actually with Mars, because we know the targets to go to, or we're pretty close to finding the targets. They're accessible within a few meters, that's what the drill's for. And we can put the instruments on a mission that goes to Mars to try and find that life too. It may well mean that we need to bring a sample from Mars back to put it in the labs on the Earth, because we need the precision. But I mean, that's one of the, don't stop exploration. But if you want to find life in the next 20, 30 years, I think the best chance is still Mars.
If that's the case, why don't you just, well, I probably shouldn't say why don't you just, because it's very expensive, but isn't it probably time for a human mission? Because you've got obviously you've got these constraints, but you go to a site and you don't find anything, so you think, all right, let's walk over to another area. I mean, with a robot, obviously it can die, but with a human, provided you've got enough life support. If you want to shoot me, I'm going to be outside in a minute. Yeah, I think I'm going to shut up now, actually.
No, it's fine.
But do you see my...
Yeah, sorry, yes. So I'm not going to argue against either robotic or human exploration. I want to see us go all over the place in all kinds of ways. You know, I applied to be an astronaut back when Tim Peake got selected, but, you know, this is the next best thing.
Okay, any more questions? There was somebody there.
I understand the ancient life on Mars will be underneath the soil. So I was just wondering as to this, in the criteria for the site selection, the aspect of just the mechanics of drilling, the types of layers and deposits and sediments on the top, and the mechanics of drilling down to try and find the ancient fossil microbes and so on.
Yeah, so I didn't go into the actual instruments and technology on the rover too much, but the main thing is it's got a drill that can drill down 2 meters and bring a core back up and put that core inside to the analytical instruments. So we have to try and pick landing sites that have widespread sedimentary, you know, layered rocks. It's not going to be, well, it's actually not a good target. We don't want to start drilling into basaltic lava flows. They're hard, and also they're not, you know, there's a low chance of life. So we have to pick those areas that look like they've got extensive layered deposits. Can drill down 2 meters, that gets through all the radiation problems of being broken down. We also target areas that have been exposed geologically recently, so last few 100 million years. And it's tough. We need the latest high-rise images where you have amazing resolution to actually see that. And we've got, you know, in most of the landing sites, actually not that many. So, you know, there's a lot of requests gone in for new images, new data. In the next 6 months, you know, we should be able to pick out the exact rock we want to drill.
Okay.
The criteria that you laid down in your selection procedure were a mixture of two things. There were scientific reasons and there were engineering reasons. And I was wondering if you just focused on the scientific reasons and chose the best possible place to go to, which engineering constraints are the critical ones in denying you access to that site? In other words, where would you, as the Director of Research in Engineering at ESA, be focusing your effort in order to get the right answer?
Do you know what? Someone asked a very similar question at the workshop to the lead engineer, and I think I'd say the answer was all of the engineering constraints are the important one. So they're the science constraints, they're all the engineering constraints that we have to match, and we got told that all of them are important. The ones that limit us in terms of the area the quickest are the elevation and the slopes, I think, and the age, the three men on the maps.
So parachutes and rover design that
yeah. And the age is actually something I've never considered before. Previous missions haven't necessarily put an age on the target. ExoMars definitely is. Curiosity had this amazing system of coming through the atmosphere where it could steer as it came through, and that made the landing ellipse very small, which meant you could hit these small targets. But I don't know. I don't know where I'd go if I had fewer constraints. To be honest, I'm probably the wrong person to ask because I listen to people talk and I'm convinced by the stories every time. We should go to Mars, we should go to Oxford. You know, I thought Gale Crater was a fantastic choice, and it's just because of the photographs that we were trying to take.
Yes, no comment. I think we're going to leave it there. Thank
Okay.
you very much indeed.